Welcome back, guys. Today we're going to talk about one of the interesting as well as the important problem in tree series, which is lowest common ancestor of BST. BST is nothing but a binary search tree. And if you guys new to BST, let me give you a quick explanation because it's very important before getting into the problem statement. So BST is nothing but it is a type of binary tree where the root node and all of its left nodes are less than the root. Okay, so root is going to be greater than the left values, all the left values. And if I tell it for the right side, so all the values on the right is going to be greater than the root. Okay, so right is going to be greater than the root value. This is the a simple definition for BST. And if you look at this tree, so let's take this is a root node. Okay, and if you look at its left children, all of its left children, you can see this is going to be less than the root node as well. And if you look at the right children, all of the right children of 6, it's going to be greater than it. So this rule apply in every level or every node. For example, I'm going to take this one. Okay, see its left side, it's going to be lesser. See its right side, it's going to be greater than it. So this is the property of BST. Now let's understand what is mean by lowest common ancestor. So in a given question, they will give node P and Q. We need to find the lowest common ancestor of it. And if they give such question, so first let me draw out the path from these two nodes, from node to the root. Okay, so I'm going to draw it. So node 0, what is the path? It's going to be like this. And for node 3, the path is going to be like this. Now 2 is going to be a common ancestor because the definition tells that the first intersection point from the bottom view. Okay, this is the common ancestor, the lowest common ancestor. So this is the first place where it get intersect, the first intersection point if you look up from the bottom of a tree. And you can redefine it as the last intersection point from the top of a tree. If you look at a tree, okay, I'm going to draw this again. So this is one intersection point. This is the one intersection point. And do you find any other intersection point? No, it doesn't. So the definition can be also like this. First intersection point from the bottom. And it can also be said as the last intersection point from the top of a tree. Okay, if you look at from the top, so this is the last intersection point. And if you look at from the bottom for this node, what is our target for this? And for this 2 node, the common ancestor, the lowest common ancestor is 2, because this is the first intersection point if you look at from the bottom. Just forgot all the theoretical explanation of it. I mean, whatever read from internet, just think like this. You just need to find the intersection place from the bottom, the first intersection place. That's it. Or else the definition can be the last intersection point from the top of a tree. So this is the lowest common ancestor. Again, if you don't understand, let me explain you guys with my previous video example, which is a family tree. Now assume this is the node P and node Q. Now tell me guys, who is the closest? Now tell me who is the closest to him. Okay, what is the first step? You're going to draw the path, right? Now, who is the first intersection point? Tell me, who is the first intersection point? Sam. So the lowest common ancestor for John and Lara is Sam. Again, you can think it like this as well. And a relation, who is going to be the most important person for node P and Q? Tell me, father or a grandfather? Who is important? So father. So likewise, you just need to find the lowest common ancestor. Again, father is also a common ancestor, but is not a closest one. So the lowest indicate the closest one. I hope you guys have some basic understanding of what's lowest common ancestor. With this in mind, let's think what is the naive solution, a brute force one. Okay, the brute force solution. So the brute force solution is going to be look like this. You already know how to do this. Okay, now let's apply the same concept. So what we did, we just find the path and did the intersection with the first intersection. So let's apply the same thing. I'm going to write the node, the path node. Now tell me guys, what is the path of 0? It's going to be 6, it's going to be 2 and 0. This is the path of 0, right? So this is how we reach this node. And now tell me for node 3 path is going to be 6, 2, 4, 3. Am I right? Simple. 6, 2, 4, 3. Now I just return over the paths. So you can just use DFS or BFS to get this paths. And what's the next step? Pretty simple. Just find the last intersection point. This is equal, this is equal. And if you look at this point getting failed, which indicate that this is the last intersection point, so that you can simply return answer as true. Sorry, it's 2. That's it, guys. Now if I want to give some more example, let me give it to you. So I'm going to change. Now tell me, guys, what are the paths of 0? So 0 is going to be same, 6, 2, 0. And what is the path of 7? How to reach 7? Simple. It's going to be 6, 8, 7. Now tell me which is the last point it get intersect. Let's both the values are equal. Yeah, it does. Now it's check next values. It is equal. No, it doesn't. Which means the previous value is the last intersection value. So the answer is going to be 6. So the LCA of 0, 7 is going to be 6. And I hope you guys understand this brute force solution as simple one. Now let's think about the time and space complexity of this problem. The time is going to be, okay, the time is going to be big O of n and big O of m. So why do I say it like that? Because you have to find the path of 2 nodes, which is going to be from top of the valley to the P node, and another node is going to be top of a valley to the Q node. So this take O of n plus m, obviously you can return it as O of n at a worst case. And what is the space? The space is going to be big O of n plus m again, because you are storing all the paths in a list. You should store in some data structure, right? So it's going to be list. That's it. This is the time and space complexity. But this solution is not acceptable in tree solutions, because you can do much more better. Obviously, this is the BST tree. You can do way better in it. Now let's figure out how to utilize the BST property and solve this problem much more efficient compared to this time complexity. Now let's see it. Now tell me, guys, what could be the possibility if I'm looking for the 2 nodes in a tree? So the first possibility is going to be that both the nodes, I mean both the P and Q, are going to be in a left side. So both the nodes are in left. Now what is the second case? I mean, what is the second possibility? So both the node could be in a left side as well, right? Let me write it down. So now what is the next possibility, guys? Tell me. It could be in a left as well as the right. So one in left and one in right. That could be one possibility, right? So one P node can be in left side and a Q node can be in a right side. That could be one possibility. The last base case is a little tricky, guys, which is node can be also an ancestor of it. So any one of the node can be it. That's the last base case. Now with this in mind, let's solve this problem. So I have just drawn a little big tree for a better understanding and better dry run. So now tell me, guys, what are the ancestor of 12 and 5? I'm asking all the ancestor, not one particular one. So the node 12's year and 5 year. Now tell me all the ancestor of it. So the ancestor is going to be 15 and 11 and 20. So these are the ancestor of this particular node. So remember the definition I said, the first intersection point from the bottom. That also tells that 15 is the lowest common ancestor of them. And don't forget, guys, this is also an ancestor, but the question asks you the lowest among them. So the lowest among them is going to be 15. Or lowest is nothing but the most closest one to this particular node. That's it. This is the very easiest explanation, I guess. Now let's apply the binary search property and do the answer. Now let me talk about this particular base case, guys, because this is very easy to understand, which tells that one node can be in a left, one node can be in the right. If this such a case, tell me which is the lowest common ancestor. This node. Am I right? Because it's just dividing it. So if it just divide like this, which could be the last intersection point or the first intersection point? This. Am I right? It's pretty simple. If I want to show an example, tell me what is the LCA for 11 and 28, which is 20, which can be shown for this base case. It's nothing but whenever it's going to getting divide, the divided parent is the LCS because it is the last point which gets the intersection, right? Previously, it might get intersect somewhere also. For example, what is the LCA for 13 and 19? It's going to be 15. The reason because 15 is the one which divide both the node, right? 15 is the one which divide both the node. So that 15 is going to be the last point where it get intersect. So that's it. This is very pretty simple base case. One is going to be node of itself. Instead of 12, let me write 20. Now, what is the LCA for 20 and 15? Sorry, 20 and 5. Obviously, it's going to be 20, right? So if any one of the node is itself, then return that particular node. This is one more base case, pretty simple. Now let's start the dry run, guys. Actually, I did small mistake in the example. So now let's take 12 and 19. Okay, so 12 is here, 19 here, and we need to find the lowest common ancestor. So 5 is wrong. Sorry for it, but that's fine. Explanation is right. Now let's do the dry run. So starting node is going to be 20. Am I right? Now tell me 20 is greater than 12 and greater than 19. Tell me. Yeah, it does. Which indicate that 12 and 19 are lies in the left branch. Okay, left branch. Remember the first two base cases, which is both the node belongs on the left or both the node belongs on the right. So this is the left part one. So now we are telling that 12 and 19 lies in the left half of the 20. So now let's move it. Now let's move down. So from this particular place, we are coming to this one. Yeah. Now we are standing at 11. Now tell me 11 is greater than 12 and is greater than 19. No, it doesn't. Base case, what does it tells? One of the base case. Both the nodes lies on the right side. Now, according to the BST property, in which side the highest value will be there? It's right. Now we need to move to the right side. So now let's move to the right side. I'm coming to the right. Now I'm at the position 15. Okay, position 15. Now tell me 15 is greater than 12. Yeah, it does. But 15 is greater than 19. Tell me. No, it doesn't. It fails. So which telling that 12 could be on the left side and 19 could be on the right side. This is the third base case, guys. Do you remember my explanation? Whenever we are just getting a splitting node, I mean the parent node is going to be the lowest common ancestor. That's it. Pretty simple. With this base case, we just reached the answer. How simple it is, guys? Tell me. Very simple, right? I'm going to take one more example as well. Let's take 15 and 22. So 15, 22. Now tell me, as a first step, what we'll do, we started from 20. So 20 is greater than 15. Yeah, it does. Thus 20 is greater than 22. No, it doesn't. Which tells that 15 is going to be lies on the left side and 22 is going to be lies on the right side. What you will do if such case happens? Pretty simple. Return the node itself, 20, because it is the splitting node, right? And we have seen example for all the base cases. Now let me write the pseudocode, guys. It's going to be damn easy. You already covered all the base cases. So while writing, it will be way much easier. And I'm not going to code this up because so simple. You can write from the base case itself. So let me start it out. As a function, you're going to get a root node as well as a P and Q node. Now, what is the first base case, guys, comes in your mind when you try to solve a tree? What if tree is empty? In such case, return null. So if not root, if there is no root, simply return null. So return null. That's it. Now let's pick the current node. So the current node is going to be integer of the current node is going to be root dot val. What's the first base case? You are checking it lies on which side of it. It's going to be lies on a left or a right side. Let's do that. If current node is greater than p dot val and current node is greater than q dot val. Tell me which side. If the root is greater than both the value, which side we need to do a search? We need to go to the left side. So let me do that. The function of root dot left. We need to do searching on a left side, right? Like this we need to go. So from this position we go on this right. Now we need to do search on this particular thing. That's why I'm just sending root dot left, and P and Q are going to be same. So P comma. So what is the next base case, guys? It's going to be lies on a right side. So let me write this pretty quickly. Then Q dot val. And if it does, what's the case? So root dot right and P and Q. Pretty simple. What is the next base case? If either one is left, either one is right. At that particular case, what I need to do, I just need to simply return the root node itself. If you want to be more specific, you can write the if condition for all this thing. I mean, remaining two cases, but I guess it doesn't need it. So return root over there. That's it, guys. This is the entire code for LCA of two particular node. Thanks for watching till this, guys. I hope I did my best to explain this particular problem as well as the pseudocode. And if you want the language specific code, it's going to be in my blog page. You can check out my blog, which is codewithmagesh.tech. I'm going to give the link in my description. You can go there. It's completely free. You don't have to pay for anything. And thanks for watching, and we'll meet again in one more video. Until then, bye.